In the last two lectures, we looked at diatomic MO diagrams for H2, F2, O2, and we've looked at central atom molecule MO diagrams, such as in CO2. The diagrams have been complicated, but all the diagrams we've looked at so far can be made in a single figure. In this lecture, we will begin to look at systems where you need two orbital diagrams, a first order orbital diagram and a second order MO diagram. So there will be a first order diagram which will set the stage for the actual MO diagram. The first order orbital diagram will use exactly the same rules as we had in our one figure MO diagram. So in this clip we'll just briefly review what that procedure is. For central atom molecules, the central atom is to the left and the peripheral atoms are to the right. For diatomic molecules, the left atom is to the left, the right atom is to the right. The diagrams are on an energy scale. We draw the central atom AOs using this energy scale, and we always draw the molecular framework. If we have a diatomic system, we put the left atom, we draw its AOs, and we again draw the molecular framework. In central atom molecules, we mix similar looking pairs of peripheral orbital AOs and place them on the right side. In diatomic molecules, we place the right side AOs on the right side. We mix them in pairs at this point. Left and right orbitals mix, and we place them in the diagram center. Bonds go down 2 or 4 V's. That's the strength of a covalent bond. Antibonds go up the same amount of energy. And for diatomic molecules, we mix similar looking orbitals, left and right. Because always, in all mixing, it doesn't matter what the system is, first order, second order, diatomic, and central. The very first mixing you'll always do will be the mixing of molecule equivalent, geometry equivalent orbitals. So molecule geometry equivalent orbitals, similar looking orbitals, always get mixed first. Okay, so in diatomic molecules, when we mix the central atoms, we're going to mix just similar looking left and right side orbitals. But with central atom molecules, we need 2 additional criteria to figure out what's going on. Orbitals from the left side and the right side that interact well, have good constructive or destructive interference, they always should be interacted first. And orbitals that are close in energy must be mixed first. So there's 2 things that we have to consider: close in energy and strong interaction. The resultant lower or high energy mixtures will resemble more initially the respective low or high energy orbitals. We'll actually study that in the next clip, but in the next clip. Here's one important fact that has always been in these rules that we haven't looked at, so I put it in red. Mixing between orbitals goes from a high when the 2 orbitals start off at the same energy, and it gets weaker and weaker as they get farther and farther apart. And by the time they're around 20 EVs apart, orbitals from the left and right side really don't mix. Mixing goes to near 0. And the final rule is that after we've done mixing, we mix the orbitals, and once an orbital is mixed, it's used up, and one side's orbitals can get extinguished first. We carry over all remaining side orbitals to the diagram center, and then we draw the horizontal lines. And if we need to, we fill with electrons.